Welcome back, kids, or adults, whoever may be listening. We're going to start Chapter 2. Chapter 2 is all about functions. So first, 2.1, we're looking at graphs to relate to quantities. So kind of leading up to functions. Our Common Core Space Standard is f.if4. One of those F's stands for functions. I think it's functions, interpreting functions, or something like that. But this says, for a function that models a relationship between two quantities, interpret key features of graphs and tables in terms of the quantities, and sketch graphs showing key features given a verbal description. So a couple different things that is happening there, but we'll go on with that. Oh, also, I guess I have to do this Q&A thing since I got 50 subscribers or whatever the goal you set was. But yeah, so stay tuned for that. We'll do that a little bit throughout the video. Alright, so this says you can use graphs to visually represent relationships between two variable quantities as they both change. So looking at this graph over here, it says it shows the volume of the air in a balloon as you blow it up until it pops. What are the variables, and describe how they are related at various points on the graph. So your variables are just going to be what's on the axis, so volume and time. Time is our x, because it's on the bottom. Volume is the y. Okay, so those are two variables, and then this red graph shows how they're related, as how the volume is related to time as it goes on. So here, at 0, there's no volume in the balloon, and there's no time. So you start blowing up the balloon, it goes up, then you have this little gap right here. Okay, it's kind of steady, so that's probably when you're taking a breath. And then you blow again, there, and then you have this other gap here. Probably taking another breath, and so on. And then what happens here? Bam, all of a sudden the balloon pops. And there's no volume, so it goes straight down to 0, just like that. Okay, so that's kind of how you can describe what's happening in this graph. So look at these two problems. What are the variables? So just length and time. What are the variables here? Minutes of calls and cost. So let's look at B here. We're talking about the June cell phone cost. So what's happening here? So it looks like your cost is staying constant for quite a while until you get to so many minutes. We don't really know. It doesn't have any numbers on this graph, so about right here. After you get to this many minutes, whatever that might be, then your cost starts going up. So you have a certain amount of minutes for free, or for a fixed cost, whatever this cost is, and then after a while, it starts going up per minute. And it is going up constantly after a certain point. Alright, so I'll answer one of your questions. Let's see. Okay, so this is a fun one. This is from Daxton Brumfield. It says, is 0.9 repeating equal to 1? So if we look at this, 0.1 repeating is the same as 1/9. 0.2 repeating is the same as 2/9. And the pattern goes on. So 0.8 repeating is the same as 8/9, and 0.9 repeating is the same as 9/9. Because it's a pattern, right? So then 9/9, actually 9/9 is just simplified to 1. So if you do have 0.9 repeating, indeed, infinitely, that should equal 1. Basically, same thing. Super fun question. Thanks, Dax, for the question. Yeah. Anyway, I'll answer some more later. Moving on. Alright, so now we have this table. It says, a band allowed fans to download its new video from its website. I'm not sure why the W is capitalized there, but it is, so interesting. The table shows the total number of downloads after 1, 2, 3, and 4 days, which graph could represent the data shown in the table. So in day 1, there was 346 downloads. Day 2, 1,011. Day 3, 3,455. And day 4, there was 10,426. So clearly, this video is getting more popular as the time goes on, because if you look at this, the first one it went up, I'm just going to estimate about 650-ish. Then it went up like 2,400, and then it went up like 7,000. So it's getting more and more popular. So this is not going to be a constant, it's not going to be a straight line pattern, because it's not going up the same each time. It's actually it's increasing more and more each time. So it's obviously not D here, because that one's decreasing. So let's get rid of that nonsense. It's not going to be the straight line pattern, because it's not going up the same each time. So then we have B and D. So if you look at B here, B does show it like increasing faster. So it's kind of increasing like this. If I was to draw a line through or a curve through it. C would be slowing down. So that means it would get really popular at first, and then it kind of dies off. So actually this case would be B. It starts out kind of slow, but then as time goes on, it gets more and more popular. So it's increasing faster as the time goes on. All right. Okay, look at this one. We're talking about the amount of sunscreen in a tube, I guess. Sunscreen tube, is that what you call those? Compared to its number of uses. So those are 2 variables here. So after 0 uses, you have 5 ounces. So that means the bottle, when it's full, is 5 ounces. After 1 use, 4.8 ounces. After 2 uses, 4.6. And after 3 uses, 4.4. So you can see here that it's going down the same amount each time. So if it is going down by the same amount each time, so minus 0.2, not only does that mean you're very consistent when putting on sunscreen, but also it means that your graph, if we were to put it to a graph, is going to fall in a straight line. It's linear is what we call it. And we'll talk more about linear functions as we go on in this chapter. But, so it's not going to be this one, because we don't use, this would be like we use a lot at first, and then, no, yes, and then it starts going down, or something like that, yeah. This one is a straight line, so it could be that one. It could also be this one, though. This is also a straight line. So what this one does is it says, okay, at 0 there's 5, cool, but then this is clear down here after like, I don't know, 1, 2, 3, 4 uses, or 3 uses. So this is 1, 2, 3. This is after 3 uses, we're at 0. So that means you're using a lot of sunscreen after 3 uses, probably way too much. So this one is only going down slightly, 0.2 each time. So you still have lots of sunscreen left here to use. Lots of uses you could use. So this one's going to be C, because it doesn't go down quite as quickly as A is going down. You're not using that much sunscreen every time. All right, I'll answer another question. Who is your favorite YouTuber? From Paige Reyes. Obviously myself, because I'm vain. But other than that, probably, I don't know, Joe on the Go. Yeah, he comes close second. So yeah, there's that answer page. And obviously I don't know really how these Q&As go, because I've never seen one, so just kind of winging it. So, alright, a couple more problems to do here. This says in problem 2, spell. Problem 2, the number of downloads, which is on the vertical axis of each graph, depends on the day, which is the horizontal axis. When one quantity depends on the other. Okay.
Jack Matthews, please report to
Hold on. Let's come back in like 1 second.
Mathis, please.
Anyway, when one quantity depends on another, show the independent quantity on the horizontal axis and the dependent quantity on the vertical axis. So your x is your independent variable, your y is your dependent variable. Okay, so we will look at how to sketch this graph from problem 3. So this says a model rocket rises quickly and then slows to a stop as its fuel burns out. It begins to fall quickly until the parachute opens, after which it falls slowly back to Earth. What sketch of a graph could represent the height of the rocket during its flight? Okay, label each section. Okay, so we're going to start with the two axes here, our x and our y. And our two variables we're looking at is height, for one. And the second one, we're looking at during its flight. So it doesn't come out and say specifically what it is, but it's going to be time. Okay, so we're looking at height compared to time. Time is almost always going to be your independent, so it almost always goes on the bottom. And then our height will go on the side here. Okay, so it's rising quickly, so we're starting at time 0, the height is 0. And then as soon as it launches, it's going up pretty quick, so it goes pretty quick like this. I'm not sure why my pen does this curvy thing it does, but it's kind of cool. But it's going pretty fast up, so we have a pretty steep line there. Until its fuel burns out, so then it starts to kind of slow down. It's not quite as steep. And then as soon as the fuel burns out, it's peaked here. Here's its peak. And then it starts to fall quickly, so pretty steep, maybe not quite that fast, but pretty steep, until the parachute opens, and then it falls slowly back to Earth. So when the parachute opens, then it starts going down not quite as fast, so we're going to make this line not quite as steep, so maybe something like this. Okay, so you can see the different parts here of this graph. Here's takeoff, this piece. Take off.
Bailey Clark, please come to the office.
Here is when it runs out of fuel, that's the peak. Out of fuel. And then at this point right here, when it changes from going down fast to going down slow, that's where the parachute opens. Parachute. Okay, so that's sketch of the graph, label each section, something like that. Okay, and there's no exact answer to questions like this, so as long as it looks, similar, or you can justify your answer, then it's probably fine. All right. Okay, so this one says, suppose you start to swing yourself on a playground swing, you move back and forth and swing higher in the air. Then you slowly swing to a stop. What sketch could represent how your height from the ground might change over time? So again, we have height compared to time. So, whoa. Height, time. If you're on a swing, when you're sitting down, you're not on the ground because no swing starts on the ground. So we're going to start like right here, off the ground. And then as you start to go swing, you're going back and forth. And so every time you go back to your starting point, you're the closest to the ground. So you're always going to come back to this spot right here. But then you're going closer, or you're getting higher and higher as you go back and forth. So it's going to look something like this. Go higher, and then it comes back down. Then you go back up, then you come back down. And then if you swing faster, you get a little bit higher until you slow down. And then it starts looking like this. But it should always come back to this same level right here. Yep. So I mean, something like that. Again, it doesn't have to be specifically that, but just know that and I probably started out a little bit too high here. Maybe it should be kind of symmetric to this side over here, but it's fine. No harm done there. But yeah, so those are how you can relate graphs to scenarios or numbers or tables, things like that. And that's how we can use that. Alright, I will see you guys next time. Continue this Q&A later. Adios.